Right. So in this class, we are going to see about the frequency response of a common collector or emitter follower amplifier. Right. So we have seen about emitter follower amplifier in our first year electronic course. Hope you have an idea about the circuit, and we have done the hybrid parameter model or hybrid parameter analysis or low frequency or small signal, small signal analysis on common collector amplifier. Today we are going to see how we can do the high frequency analysis, right? Or the properties or the frequency response of a common collector amplifier at high frequencies. So first, okay, let me draw the circuit diagram of a common collector amplifier, right? So we have VCC. Can you see the text? Is it clear to you?
Yes, sir.
Okay, done. Right. So yeah, sorry, that will be. So there is no RC, right? So this is an NPN transistor. Here we have our RL, which is grounded, and then we have a potential divider for biasing the transistor. Right, for biasing the transistor. And this one, we have a bypass capacitor. This will be our V out, right? This will be our V out, where this is my load resistance or emitter resistance at common collector configuration, right? Of course, here we have a capacitor, and then we may have an internal resistance and a AC source, right? Internal resistance may be C in, right? This will be C out. This is R1 and R2, right? So this is the common, okay, this is PPS, right? So this is the circuit diagram of a potential divider bias common collector or emitter follower amplifier, right? So we have an AC signal and a DC current sources across this one. Right now, okay, let us draw the high frequency equivalent circuit of a transistor, right? High frequency equivalent circuit of the or hybrid pi model for the common collector amplifier circuit, right? Okay, first of all, I'll draw the equivalent circuit of the transistor itself, right? Of the transistor only, right? So here we have the transistor, so I'm going to draw the equivalent circuit of the transistor, and then we'll connect the external circuits, right? Okay, so first of all, yeah, okay, right? So this will be your Rx, and then R pi, C pi, right? This one we have seen it in our last class, right? C pi. Then of course I have another capacitor which is C mu right here, Gm into V pi, right? Where V pi is the voltage across these 2 points, right? Right? V pi, Gm into V pi, right? So that's all about the transistor. So this is your collector terminal. The whole is your emitter. This one is your base, right? So emitter, collector, base. Right now, what we can do is, right, to draw the hybrid equivalent circuit, the first thing we have to do is short circuit all the capacitors. So this can be short circuited, and this one can also be short circuited, right? So those two capacitors eventually will be removed from the circuit, right? Will be removed from the circuit, and ground any DC voltage sources you have, right? We don't have any DC current sources, so leave about it. There are no inductors, leave about it, but we have a DC current source, so just ground it, right? So we can remove it and then we can ground it, or else we can delete this line and we can make two ground lines, right? One ground here, the other one is here. So what I can do simply is, instead of this one, I can replace with a circuit something like this, right? So there are two grounded terminals, and then here also, yeah, this is grounded everywhere, right? So now look at here, we'll complete the circuit in the model, right? We'll complete the circuit in the model. From collector, right? This is your collector, right? Collector, emitter, and base. Collector is directly grounded. Am I right? Collector is directly grounded. So what I can do is, right, and then from emitter, I have RL and that is grounded, right? From emitter, of course, I have RL and grounded. Right, RL and grounded. Similarly for base, right, so of course, right, so I can assume that this is grounded, this one is also grounded. Simply I can fold this one, right? So ground equipotential points, so I can join together. So I may have two resistors which becomes R1 and parallel R2, right? So from base, right, to ground, I have a resistance which is R1 parallel R2, and then from base I have my RS, VS, and that is also grounded, right? So from here RS, VS, and that is grounded, right? That is grounded. So what I can do is simply I can connect these two grounds, and of course look at here, the C is grounded, right? C is grounded. So what I can do is I can remove this one, I can make it something like this, right? This is grounded, so simply this is also ground, this is also ground, so I am connecting it to this, right? Okay, now let me simplify the circuit, right? Okay, look at this circuit, right? Forget about this ground, right? Forget about this ground. So now we have a circuit something like this. Of course, R1 parallel R2 will be much higher, right? It's a very big value, right? It's a much bigger value. So that can be neglected, right? That can be neglected. And then look at here. This is short circuited, and then we have R here, right? We have R here, which is connected from emitter, right? This one GM into V pi, and then this one, right? Okay, now consider that one. So this is my collector, right? So this is my collector means this is also collector, right? This is also collector, right? I can assume that this one as my collector, but all of them are short circuited, right? If this is ground, 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 I can simply fold this one, right? Fold this one from here to here, right? Can you understand? While I'm folding this one, right? How can I explain it to you? Right. Just imagine that I'm just pulling this one here, right? So this is grounded, right? So what I can do is, right? So this is ground, right? This is zero potential line. Can you see that? Yes. So I can make it something like this, and I'll make this one as a ground and this is as a ground, right? These two as a separate grounds. So what I can do is I can fold this one upside down, right? Because this is grounded, right? So this becomes, right? So the current is from top to bottom. So when you are folding it down, the current direction will become bottom to top. Am I right? GM into V5. Now the current become bottom to top. Right. So this point is here. Now this is grounded. So I can bring this C here. Right. I can bring this C here. Right. So C is connected to this point, any point. So I can connect my C here. then I can draw my C mu somewhere here, right? And then just turn this one, right? Turn this one. I'll redraw the circuit, right? I'll redraw the circuit. So now I don't have this one, right? So which is R1 parallel R2, which can be removed from your circuit. So now I have my RS VS, right? So this is my RS, and then R pi, RX, and then from RX, this C mu comes, right? C mu comes, which is to ground, right? C mu that is connected to ground. Right, from here to the other point, we have R pi, C pi, which are parallel, and the voltage across R pi and C pi is V pi. Right now, just turn this one, right? Just turn this RC parallel component into this shape. So I may have R pi parallel C pi. Right, R pi parallel C pi, and of course the voltage across R pi and C pi is denoted by V pi, right? Remember, right? The voltage across these two parallel component is given by V pi. So I am marking it by this one, and then look at here. So this point is here. So we have Gm into V pi, but the current direction is changed, right? The current direction is changed. It is not top to bottom anymore. So we have, right? So this will be Gm into V pi, where V pi is this voltage. Then here I have my RL or RE, right? RL or RE, and this will be my V out. Clear? Any doubts? If you have any doubts in drawing this circuit, please let me know now, right? I'll just make it clear, and then we can move to the next step. Without understanding or without knowing how to draw this circuit, we cannot go to the next step. Right? Any doubts in this? No doubts.
No, sir.
Okay, right. So now we'll move to the we'll move how to do the derivation based on or how to calculate the gain from this circuit, right? So okay, now we'll have a point, right? Let this take this point as capital A, right? This as A and this as point B. Right, this is point A and point B, right? So what is the voltage at point B, right? Let's take this as ground, right? Assume it as ground. So what is the voltage at point B? Will be V out, right? If this is ground, of course the voltage at this point will be V out. Of course current is going to flow, right? If this is top to bottom, so RL current from here to here, so this one will be simply V out. And what is the voltage at point A? What is the voltage at point A? Simply V out plus V pi. Am I right? V out plus V pi. Right? Okay. Now we'll do the calculations, right? So, okay, for your easy, I can do another thing. Right. So make sure that we have a current here, right? Let this be I1, right? So here another current which is I2, and here another current which is I3, right? We have three current components at this point, and similarly here we are going to have I3, and here we have Gm into V pi, and then here we are going to have I out. Clear? We are going to have I out, right? So now we'll let apply Kirchhoff's current law at point A and B. Right. First, we'll apply Kirchhoff's current law at this point. Right. At this point, let's take the voltage at this point as VA. Right, for simplification, and this as VB. Right. This is VA and VB. So, what is the current I1? What could be the current I1? I could say that here the incoming current is I1, outgoing current is I2 and I3. So I1 minus I2 minus I3 equals 0. Am I right? By applying Kirchhoff's current law at point A, right? Sorry. By applying Kirchhoff's current law at point A, right? At point A, I would simply write I1 minus I2 minus I3 equals 0. Am I right? I3 equals 0. So what is my I1? I1 will be, the voltage at this point will be Vs minus Va divided by Rs plus Rx. Right? So I1 will be, right, Vs minus Va divided by Rs plus Rx minus, what is I2? I2 will be VA, right? The voltage across the capacitor will be VA. VA by 1 over j omega C mu, right? Only we have a capacitor. So minus VA by 1 over j omega C mu. Right, 1 over j omega C mu, and minus, what will be my I3, current I3? I3 will be, of course, we have V pi, right? We have current I3 will be V pi, right? The voltage across these two parallel components will be V pi divided by the parallel component of this one, right? Parallel component of this one. Or I can simply write, right, in this one, let's take it as Z pi, right? R pi parallel C pi. So I can simply write 1 over Z pi equals 1 over R pi plus 1 over j omega C becomes j omega C pi. Am I right? J omega C pi. Right? So when this becomes, so the voltage I3 equals V pi divided by Z pi, or V pi into 1 over Z pi. Am I right? So V pi multiplied by the whole term. Just substitute here, right? So this will be yeah, V pi into 1 over R pi plus j omega C pi equals 0. Clear, right? So this is the first equation we have before going into the next step. Right now, we'll come into this one. Right? We'll come into this. Right? So this will be V out. Am I right? If I say in simple words, I could say that. Right? So I'll go back into the other notations. Right? So V equals V out. Am I right? VB will be equal to the output voltage V out, and right, and VA equals V out plus V pi. Am I right? V out plus V pi. Right now we have two equations, and substitute VA, which is equal to V out plus V pi, right? This one in this equation, right? So this will be an equation in terms of V out, V pi, and Vs. Am I right? Now substitute VA as V out plus V pi. Right, so now this becomes, if I rewrite this one, right, so Vs minus V out plus V pi divided by Rs plus Rx minus, instead of Va again we'll substitute this one, right, V out plus V pi divided by 1 over j omega c mu, right, minus v pi into 1 over r pi plus j omega c pi, which is equal to 0. Right now, look at here. You can take v pi, right? V pi as common. Yeah, we can group them, right? We can group v pi separately, v out separately, and vs separately, right? So let this be okay. So here we can write it as of course, yeah, vs by rs plus rx, right? So vs plus rx minus, okay, now group v pi together separately and then v out separately, right? So now we'll make it v pi into, right, here I have a v pi which is minus v pi, of course that can be directly taken as plus, right? So that becomes 1 over rs plus rx, rs plus rx, right, again minus v pi into j omega c mu, right, plus j omega c mu. Again here we have a minus, so that becomes plus j omega c pi plus 1 over j r pi, right? So j omega c pi plus 1 over r pi. Now group V out separately, right? So we have a V out into j omega c mu and minus V out into, sorry, both minus, right? So we'll put minus V out into, right? So here minus V out into 1 over Rs plus Rx, 1 over Rs plus Rx plus, right, here we have a minus, so that becomes minus here, so that becomes plus j omega c mu, j omega c mu, and that is equal to 0. Clear the whole equation, so I'll put equal to 0 here, right? The whole equation is equal to 0. Right, now what we can do is, there are two minuses, so I can put an equal sign and make it plus. Am I right? Am I right? So since this is equal, just there are two minus signs, so just bring it away from the equal. So this becomes, so Vs divided by Rs plus Rx equal to V pi into the whole term, V out into the whole term. Right, now what we need is, we have to calculate V pi, right? We need V pi in terms of Vs, so V out, and then substitute in this equation, you will get the answer. right? So we'll keep this one separately. Then we'll apply KCL at another point to calculate the Kirchhoff's current law, right? So let's apply Kirchhoff's current law at this point, right? At point B by applying KCL, Kirchhoff's current law at point B, right? At point B. So here I can simply say, right? So the incoming current is these two, and outgoing current will be my I out, right? Let's take this as I out. So these two are going inside and I out is coming out. So I can say that I3 plus, let this be I4. I3 plus I4 equals I out. Am I right? So I3 plus I4 equals I out. Right? I just put the equal sign the other side, right? So here I4 is Gm into V pi directly, right? I4 is Gm into V pi. I3 is this one, right? V pi into C pi, which is this one, right? So I can directly write it as, instead of I3, I can write, V pi into 1 over R pi plus J omega C pi, plus I4 will be simply your Gm into V pi, right? Which is equal to the output current, right? I out will be simply V out divided by RL. Am I right? I out, if I apply Kirchhoff's voltage law, or sorry, simply Ohm's law, I out will be the current through the load resistor. If it is V out, I out will be V out divided by RL. Right? So now we have a equation something like this, right? We have an equation something like this. Okay, now we'll rewrite this equation, right? We can rewrite this equation. Of course, V pi is there, so we can make it here. So I can write this as V pi into 1 over R pi plus Gm plus J omega C pi equals V out divided by RL, right? V out divided by RL, right? So here you have Gm, right? The transconductance value, right? When compared to Gm, your omega C pi can be neglected, right? This can be neglected. So again, when you are calculating the mod of these resistance, these has to be squared, right? So we can simply neglect this value from your equation, right? The imaginary part can be removed from the equation. So we can rewrite this as V pi into 1 over R pi plus Gm equals V out by RL, right? V out by RL. Or simply, I can write my, right here, either you can calculate V pi, right, from here and substitute the whole thing here, or V out and you can substitute the whole thing here to get V out by V S, right? So the easiest way is to substitute V pi as a function of V out. So simply you have V out, take it common and then bring it the other side. So Vs by V out, you can easily get the gain V out by Vs. So now we'll calculate V pi from here, right? V pi from here. So I can write it as V phi equals V out divided by RL, right, into 1 over GM into plus, sorry, 1 over R phi. Clear? GM into 1 over R phi. Right. Now, substitute the whole term, right? Substitute the whole term instead of V pi here. Right. So this is the V pi. We have another equation here. Just substitute here. V out. You can take V out common, and then we have Vs, right? Vs. So our voltage gain AV will be V out divided by Vs, right? So I'll leave the simplification for you, right? It's a bit complicated, right? But I'll leave it to you, right? You guys have to try it, and in the next class you have to give me the equation, or you can simply complete the derivation for me and you can upload it in Google Classroom, right? I will create a Google Classroom account separately and you can upload it, right? So I will complete the derivation next week, right? Next class. So now what you have to do is substitute this one here. It is simple, right? Nothing wrong with this one. So you will get a function, and then change the function into, right, you will get an equation which is for V out by Vs, and then write that equation in the form of AV mid divided by 1 plus J omega over omega h, and then from there you can calculate AV mid and omega h of a common collector amplifier. Okay, so this is for your practice, right? This is for your practice. Substitute this one, calculate this one, rewrite the equation in this form, and then find out midband voltage gain AV mid and upper cutoff frequency omega h. Okay. Any questions or any doubts you can ask me now, right? Please feel free to ask questions. No questions? Okay, I will upload the recording in YouTube, right? And then you can refer it and you can complete the derivation, right? You can complete the derivation, and I will complete it after you guys have completed it next week, right? I will complete it, definitely. I'll keep all these papers with me, and then I will complete the derivation for you in the next class. Right, now we'll move it into field effect transistors, right? The next section. Right, so we have started at 9:30, right? So okay, we have another half an hour. So I don't think, yeah, we can finish it, right? We can go through it. Anybody have classes at 10 o'clock? Hello?
No, sir.
Okay, so shall we continue?
Okay, sir.
Yeah, okay, right. So field effect transistor, right? The high frequency analysis of a field effect transistor. Right, high frequency analysis of FETs, field effect transistors. Hope all of you have studied about field effect transistors, right? Okay, I'll just briefly recollect the basics of a junction Jfilt, right? Not the MOSFET. I'll just briefly go through into the structure of Jfilt, right? So you know that Jfilt is just a piece of crystalline semiconductor with gate, right? A wraparound gate, right? You can assume that the channel is like this one and the gate is a wraparound, right? It will be kind of a rolled off. So if it is there are two types. If the channel is N type, made up of N type semiconductor, so this will be N and your gate will be P plus, right? Heavily doped P region. If your channel is P type, and then your gate will be heavily doped N region, right? So this is called as N channel FET. So these are ohmic contacts. So I have source and drain, right? So this will be my source and drain. So this is my gate, right? This is my gate. Since I have Pn, I will have a depletion region, right? I will have a depletion region. I have a P plus semiconductor and N type semiconductor. So I'm going to have a depletion region across this Pn junction, right? So now whenever, so this is P plus, right? So I would say this is P plus, right? P plus semiconductor, right? So if I apply a positive voltage at gate terminal, then this, I could say that this is a PN junction, right? If I apply a positive voltage, this PN junction is forward biased, and if I apply a negative voltage, then that will be reverse biased, right? If I apply a negative voltage, this PN junction will be reverse biased, and when it is reverse biased, of course our depletion region will get grower, right? So since we have a wraparound gate, we will have depletion regions both sides, and effectively when we are increasing the voltage, the depletion region is growing, right? It will grow, and at one point at Vg equals Vp, the depletion region will cover the whole channel, and there will not be any current through Is to Id, right? So that is called as pinch off, and this is Vp, right? That is called as pinch off. And then we have the voltage at pinch off is happening is called as pinch off voltage, right? So of course we have seen about the properties, right? We have seen the transfer characteristic of a field effect transistors and the output characteristic of a field effect transistor. Of course, we don't have any input characteristic. Of course, yeah, it can work as a simple diode, right? One of the main advantage of field effect transistors is there will be very low current across gate and drain source, right? Gate and channel, right? In BJT, we have base current, right? IB, which is going into the transistor and joining with the collector emitter current, right? Joining with the collector emitter current, and then your emitter current will be IB plus IC. But in field effect transistor, your input side is almost completely isolated from the output side. Only a leakage current, only a reverse saturated current of this PN junction, or a very small leakage current. Or I can say that the gate drain resistor is very high, right? The gate resistance will be kind of, I would say, infinity, right? I would say infinity, but still, as I have a depletion region here, I am going to have some virtual capacitance when the field effect transistor operates at high frequencies. Right now, let's see the equivalent circuit of a field effect transistor, right? So we have seen the equivalent circuit of a BJT, right? Bipolar junction transistor, since it is and also, yeah, BJT is a, both carriers are contributing in current, right? Both minority and majority charge carriers. But in field effect transistor, only the majority charge carriers plays the role. If it is N channel, the electrons dominates the conduction. If it is P channel, the conduction will be dominated by the holes in the channel, right? Okay, now we'll see the equivalent circuit of a field effect transistor. right? Similarly, we have a gate, right? Gate here, right? So gate here, and then source here, right? We'll make D on top, right? I'll make it as that is BS and D, right? Drain and source. So this will be our S, right? Source, this will be my gate. And as I said earlier, we have a resistance between gate and source, but that will be very high, right? So we will have a gate resistance RG, right? Normally this RG is in terms of mega ohms, right? So whenever we are doing circuits or examples, we can neglect this RG from our calculations. And since we have a depletion region, we are going to have a capacitor as well, which is, we can call it as CGS, gate source capacitance. And then we have a gate drain capacitance as well, right here, gate drain capacitors as well, which is connected to, right? This is C, G, D, and this is our drain collector, right? Since still we have our GM into VGS here, GM into VGS. In BJT, we had GM into V pi, where V pi is the voltage across this one. Here is also similar, but this voltage is referred as VGS, or gate source voltage, right? And then we have a resistance of the channel, right? The effective resistance of the channel, which is mentioned by small r d, right? So I could represent this one with small r g, right? Gate resistance, and this will be small r small d, right? So this is the effective resistance of the drain, right? This is the capacitance induced between source and gate, and then gate and source. Here I have resistance. When we are solving or when we are doing examples, of course we can neglect this Rg as it has very high values, right? So now this is the equivalent circuit. Okay, we'll solve a simple common source amplifier and source follower amplifier, right? Jfilt amplifiers at very high frequencies, right? We'll do the, or we'll do the calculation for high frequency analysis of junction field effect transistors, right? Okay, so we'll start with right. So okay, let me draw the circuit diagram. Right. So we have a JFET, which is an N-channel JFET, right? So the current is going inside. V out, and then from input side, yeah, the field effect transistor could be biased with this will be my VDD, right? VDD, right? And it could be biased with a potential divider bias, so I may have my R1 and R2, which is this one, and then RS and VS. Right, RD. Right, remember we have another RD in the equivalent circuit, so I used small r, small d. The drain resistor, I can use capital RD, and this could be, yes, RS, right? Rs, and this is bypass capacitor Cs. Right? Now we'll draw the equivalent circuit first. Right. So right, we'll start with this one. Right. Of course, we can remove this one. Right. We can draw the equivalent circuit without the Rg. Without Rg. So my equivalent circuit will be for field effect transistor will be, this is my gate, then here I have my capacitor, right? This will be C G D C G S GM into VGS. This will be RD, right? So this one will be my drain terminal. This will be my source terminal, and this will be my gate terminal. Right? Okay, now we'll do the measurements here. Right? First, what we need to do is short circuit. Of course, there will be a capacitance here, input filtering capacitor, output filtering capacitor, and bypass capacitor. So just short circuit all the capacitors, short circuit this one. While you are short circuiting, RS will be removed since you have a short circuited parallel path. Right? And then, of course, we need to ground VDD. So you can ground this one, ground this one. So simply this will be removed. Am I right? So we'll complete this one. So you can fold this one upside down. So this becomes R1 parallel R2. Again, that is a very big value. So you can neglect it, but I'll do that one, right? So since this is short circuited, okay, I'll go one by one, right? So now all these are grounded from drain, right? This is my D to RD to ground, right? So this is my drain. So I have my RD and that is grounded, right? And then my source is directly grounded. So source is short circuited, right? Since at gate I have R1 ground and R2 ground, so what I can do is I can have a single resistance which is R1 parallel R2, and that is grounded, right? And then from there I have RS and VS. From gate I have RS and VS, and this is simply short circuited, right? Since and this one is also grounded or connected here, right? So now this is much simpler, right? So simply what I have to do is I can fold RD upside down to bring it across source and drain, right? Simply holding this one, right? So this will be joined together since it is short circuited, right? So and this one can be removed from your circuit, right? So now your final circuit will be gate RS VS, then CGD CGS, GM into VGS, right? Here I have this RD, right? Small RD, and then another parallel RD, and this will be my V out. Vs and V out, of course. So now what I can say is all these things is inside the transistor, am I right? All these things is inside the transistor, and what we have is Rs and Vs and Rp sorry, RD, the drain resistance, which are connected outside of the transistor. Clear? Right. Now, okay, we'll apply the same equations, right? First, Miller's theorem to divide this capacitor. And of course, since it is a very low value, right, when compared to CGS, we can neglect the output capacitance, and that becomes CT, right? So CT, and we can do the calculations, right? Right. 10:23. Yeah, still we have time, right? I'll complete this one. We'll complete the calculations, and then we'll do the rest in tomorrow's class. Right. So now look at here. So this is, I would say, minus GM into VGS, right? GM into VGS. So first, what we have to do is forget about everything else, right? Forget about the transistor. Consider this two-port network, right? Forget about everything else, right? Forget about everything else. Only for this transistor itself, apply Miller's theorem to divide this capacitor into two, right? Apply Miller's theorem, right? Just you can hide everything, right? So apply Miller's theorem. So to calculate V out, um, to calculate V out, what we can do is we need gain, right? Using Miller's theorem, we need to calculate the gain, right? So we can, yeah. So what we can do is, yeah, we'll consider it as a parallel component, right? R1 parallel, RD parallel, RD. Normally, RD will be at least 10 times bigger than capital RD, right? So this one, if it is about, this will be in terms of 40 kilo ohms and above, this will be about 4 kilo ohms, right? 4 to even sometimes, yeah, 1 to 4 kilo ohms, right? Typically, this will be 1 to 4 kilo ohm. If you want, you can simply neglect this one by assuming that RD is much bigger than capital RD, right? But if you don't want to neglect it, you can simply take it as a parallel component and mark it as ZD, right? ZD, right? So we'll do it again, of course, by calculating this, considering this as a what I can do. Okay, we'll do it as ZD, right? So we'll make it as a single resistance instead of these two, which will be ZD, right? So now I can write that now ZD is equal to RD divided by RD plus RD. Am I right? Instead of this one, I have one single resistor, right? One single resistor. Instead of having these two resistors, I have one single resistor, right? So I can say that this is my VGS, right? CGS. And this will be my VGS. This is my VGS, and this is my V out, right? So before going to apply Miller's theorem, I need V out divided by VGS, right? So V out will be minus GM into VGS, right? Minus GM into VGS, since we have plus here, right? But the current is going in the opposite direction. So V out will be minus GM into VGS into ZT, right? ZT divided by right, divided by VGS. My gain will be minus GM into ZD, right? ZD. If I apply Miller's theorem to this capacitor, similar to your common common emitter amplifier, and you can refer the Miller's theorem, so I can divide this into an capacitance at the input side and a capacitance component at the output side, right? So the capacitive component at the input side can be written as C in, I can write it as, right, C G D into 1 minus, so that becomes plus GM into ZD, right, GM into ZD, right? So I have a parallel capacitance here, which is GD into 1 plus GM into ZD, and then I have a CGS, so I can say that the total capacitance CT can be written as CGS plus CGD into 1 plus GM into ZD. Here, the GM into ZD will be a much bigger value, right? GM into ZD will be a much bigger value, or simply you can say 1 or GM into ZD is very much greater than 1, and hence we can rewrite this equation as CT equals CGS plus CGD into GM into ZD, right? GM into ZD, right? So now this circuit becomes simpler, right? So this capacitance will be removed, so I can redraw the circuit something like this, right? So I have my RS, VS, and then I have my capacitance CT, and of course there will be no capacitance here, and then this will be GM into VGS, and this will be my ZT. Right, clear. Right, so now this is my final circuit and this is my V out. Okay, I'll give this one as a practice for you, right? Now, what is your V out? What will be your V out? Okay, I'll just start this one, right? I'll start this one, right? But you have to complete the derivation, right? You have to complete it and you have to submit it. Write it in a paper, take a photo and upload it, right? So what will be your V out? What will be your V out? V out will be minus GM into VGS into ZT. Am I right? Minus GM into VGS into ZD. And then this is your VGS. Am I right? So what is your VGS? This is a potential divider. Am I right? RS and CT. Right? So VGS is the voltage across CT. So this is VS. So calculate what VGS in terms of VS, RS and CT and substitute that one here and bring the VS the other side. You will have your answer as V out by VS, and rewrite the equation in the form of AV mid divided by 1 plus J omega by omega H, and from that you can easily calculate omega H and AV mid. Clear, right? So from here you will have something into VS. Am I right? Something into VS. Substitute that one here. Bring this VS this side. So you will have V out by VS, and you will have a function, right? And then rewrite that in the form of AV mid divided by 1 plus J into omega by omega h. Clear? J into omega by omega h, and from that calculate AB mid and omega h. Right? So I have two questions for you. Right? Complete it yourself. I will upload the video now. Right? I'll upload it now. You have to complete the derivation of the common collector amplifier and um, common source amplifier as well. Right? Just take a photo and upload it in Google Classroom. Right? I will send you the Google Classroom link to your WhatsApp now. Okay. Any questions? Time for questions. If you have no questions, we can wind up the session, right? Any questions?
No, sir.
No. Okay. Right. So I'll upload